Okay, so let us now try to solve problems in elasticity, which is what we intended to do in the first place when we started this course. So at last we have reached there. So the simplest kind of elements for 2D problems in elasticity are the so-called three-noded triangles, which are also called linear triangles or constant strain triangles. Why they are called constant strain triangles, we will understand in a moment. Now, imagine that there is one such triangular element. So you have divided your mesh, you have divided your domain into a mesh consisting of only three noded triangles. 1, 2, 3 are the local node numbers of one such triangle, and there's an x and y axis which is not necessarily aligned with the triangle. So there's an x and y axis, which is the global x and y axis, and with respect to this global x and y axis, node 1 has nodal coordinates x1, y1, this is x2, y2, and this is x3, y3. These are the nodal coordinates in the global coordinate system of the three nodes of this triangle. Now, each node, since this is a two-dimensional problem, we are solving for the x displacement and the y displacements. So each node has x and y displacement, which we are going to denote by u1 v1, u2 v2, and u3 v3. This is how we are going to denote the displacements. So this has altogether 3 nodes and 6 degrees of freedom. So 3 nodes per element and then 6 DOF per element, that is 2 DOF per node. So this is the definition of this element. Now we can use our old friend the assumed displacement method, so that we assume some kind of displacement variation inside this triangle. A priori we assume that the displacement is bilinear. What we mean by that is there are 6 degrees of freedom, therefore we can choose displacement variations which have 6 undetermined constants, and then we try to determine these constants just like we had done in the 1D case. So now that there are 2 displacements, u and v, so u at any point xy inside the element is given by a1, a2 x plus a3y, and v at the same point inside the element is given by b1 plus b2x plus b3y. So we have taken a linear variation in x and y. That is what we can take if we have 6 constants. We will see later that we could have taken different functions for u and v, but that's not a very smart idea in these kinds of problems. We could have also skipped the y term and taken, let's say, y square or taken xy in these expressions. But that too will not be a very smart idea, because we need to take balanced polynomials in u and v. In the x and y directions, we need to take balanced polynomials, and we also need to take something known as complete polynomials. We will see how that affects our solutions. We will see that towards the end of this week's lecture. So anyway, these are the 6 constants that we need to determine, and these are our assumed displacements. Okay, now we can write u and v together as a vector, and as usual we call it bold u. So bold u is a vector. It's a 2 cross 1 vector, and its elements are u and v at any point inside the element. And then we can write this as so the first one, so we can first write the vector of undetermined constants. So these are the 6 undetermined constants, and this we will call a as usual. And then these two equations can be written as, the first equation has only a1, a2, a3, so this would be 1, x and y, so that gives me the first equation, and the other ones would be 0. Similarly, the second equation has only b1, b2, b3, so the first three will be 0, and this will be 1, x, y. So this is the matrix that connects the undetermined constants, the 6 undetermined constants, to the displacement at any point inside, at an arbitrary point inside the element. Now we demand that okay, if this is how the displacement varies over the element, then at the nodes 1, 2 and 3, these values must be u1 v1 at node 1, u2 v2 at node 2, and u3 v3 at node 3, which means that if I put in place of xy, if I put x1 y1, I should get u1 and v1. If I put x2 y2, I should get u2 v2, and x3 y3 should give me u3 v3. So that's what I'm going to demand from this equation, and I am going to now define a vector of nodal displacements. So this is going to be a 6 cross 1 vector which has u1 v1, u2 v2, u3 v3 as its elements. So this is 6 cross 1. So this is a vector of nodal displacements or nodal degree of freedom values that we are supposed to determine. Now, having defined this, we can use this equation now to find u1, v1, u2, v2, u3, v3 in the usual way that we have done for 1D elements. So this is your capital U, this is your capital U, and it is u1, as I said, it's a 6 cross 1 vector, u1, v1, etc. And then for u, to get u1, I have to put x1, y1. To get v1, I have to put x1, y1. For v2 and u2, I have to put x2, y2, x3, y3, and so on. So this is already defined, and this I call capital A. So the vector of nodal degrees of freedom can be related to the vector of the unknown coefficients of my assumed displacement by this, provided again A is invertible. So we still have not proved whether A is invertible or not, but assuming that it is invertible, you can write A in terms of the vector of nodal displacements. Now, once you have done it, then you can go back to this equation, and in place of this you can write A inverse U, which means now you have displacement at any point inside the element in terms of the vector of nodal degrees of freedom. So obviously this whole thing is the interpolation matrix which interpolates the displacements at the nodes, displacement values at the nodes, to any point inside the element. So this must be our shape function. This must be our shape function. So now we want to figure out what is the relation between capital U and the strains. So to do that, we will write the strain as a vector. So we'll write it as epsilon xx, epsilon yy, to epsilon xy. Remember, we had talked about plane stress and plane strain problems, and for plane stress and plane strain problems, both cases, we add this 2. I'll discuss it in a moment. We add this 2 for the shear stresses, and we solve for only these 3 components of strain and the corresponding components of stress, because there can be one component of strain or one component of stress depending on plane stress or plane strain that is still required, but that component will be dependent on the in-plane components of strain or stress, as the case may be. It's not an independent component, so we don't solve for epsilon zz in the plane stress case or sigma zz in the plane strain case. We don't solve for it. And we write the strain matrix in this way, which as you remember is written in terms of displacement as del u del x, del v del y, and then del u del y plus del v del x. This is how you write the strains. Now I have the displacements. Remember, these displacements are u and v, and I now want to find the other important link in the finite element formulation, which is the B matrix, which connects the nodal displacements to the strain at any point, strain being this vector. Okay, in this case a 3 cross 1 vector. So it's a 3 cross 1 vector. This we know is a 6 cross 1 vector. This is 3 cross 1. This is 6 cross 1. So your B has to be 3 cross 6. So B has to be a 3 cross 6 matrix, which we will now formulate. Now here is how it goes. This is our strain vector, which we have defined as epsilon xx, epsilon yy, and 2 epsilon xy in that order. And these are the strain displacement relationships corresponding to xx, yy, and xy. And we can write this in terms of an operator matrix. So the first equation we can write as del x 0 of uv. So this operator operates on u. This is 0, so you get the first equation. Similarly, you get this as the second equation, and the third equation is this. So this is the operator matrix that operates on the displacement vector at any point to give you the strain at that point. So this is the strain displacement operator. Now to get the strain displacement operator, we can now go back to our assumed displacements. Remember, u is a1 plus a2x plus a3y. So del u del x is a2, just a2. Similarly, v is b1 plus b2x plus b3y. So del v del y is equal to b3. Del u del y, on the other hand, is a3, and del v del x is b2. That means you can now write this in terms of the coefficients this coefficient vector was called A, and if I now want to write this, write these three expressions, this and this, in terms of this coefficient vector. First one is just del u del x, which is a2. So I'll have 0 1 0 0 0 0. That gives me a2 as del u del x. So I'm trying to write epsilon here. So this is what I have. Then I have the second is del v del y. So del v del y is b3. So 0 0 0 0 0 1 is what the second one is. The third one is del u del y plus del v del x. Del u del y is a3, so it is 0 0 1, and then it's b2, it is 0 1 0. So this is the matrix that connects the coefficients, the undetermined coefficients of the assumed displacements to the strain at any point, and we already have the relationship between this and the nodal displacement. So we can replace this A by A inverse u. We can replace this by A inverse u, and as a result, so we can So we can replace this by A inverse U. As a result, this whole matrix, including the A inverse, connects the nodal displacements to the strain at any point. So this must be our B matrix. So this is our B matrix. So our B matrix is a constant matrix. Remember, A is a set of is a matrix which depends on the nodal coordinates. So they don't depend on x and y. They depend on the nodal coordinates. So it's a constant matrix. And then here also we have a constant matrix, which remember comes from the fact that our assumed displacements were of this form, where our assumed displacements were linear functions of x and y. And that's why this matrix that we get here is a constant. And our B matrix is also a constant, which means that the strains inside the element at any point inside the element is the same. So it's constant over the domain of the element, which is not surprising because we have taken a linear displacement approximation, a bilinear displacement approximation, which leads to a constant strain. And because it leads to a constant strain, this three-noded triangle is also sometimes called the constant strain triangle, or CST. Okay, so it's called the CST. And now we have both the ingredients that we need to formulate the stiffness of this element. So we have the N matrix, and we have the B matrix. By the way, the N matrix, the size of the N matrix, so this is 6 cross 6. So A inverse is 6 cross 6. This is 2 cross 6. And therefore, the N that you get is also 2 cross 6. So N is a 2 cross 6 matrix. B, as we have seen, is a 3 cross 6 matrix, because this is 3 cross 6 and this is 6 cross 1. This is 6, sorry, this is so this is 3 cross 6. This is 6 cross 6. So in the end we have B as a 3 cross 6 matrix. So B is a 3 cross 6 matrix. Right. So B is a 3 cross 6 matrix. N is a 2 cross 6 matrix in case of this particular element. And now we can go ahead and make the usual steps, go through the usual steps and formulate the stiffness matrix. Okay. Now to do that, as I have mentioned before, we take this as the ordering of the strains, and we call it epsilon. We take the ordering of the stresses in the same way. Remember, no 2 here, 2 only in the strains, shear strains. And then if you want delta epsilon, then you will take delta of these. Right, similarly U is UV, so that delta U we still need to know what these deltas are. Remember, these deltas are errors in the strain that you make, that result if you make errors in displacements of delta U and delta V. So delta U and delta V are the basic independent variables here, and delta epsilon X, delta epsilon Y, etc. Need to be derived. It's easy in this case. In linear elastic finite element, it's easy, but it's not always so. So we'll spend a little time on that. But before that, let me show you how these are connected. So U has been discretized as this. So U has been interpolated using this shape function, which we have said is a 2 cross 6 matrix. So delta U will be N delta U. So these are the nodal variational displacement. So this is del U1, del V1, del U2, del V2, and so on. Remember, the del U, del small u is also a function of x and y, and therefore the value of del small u at any point inside the element will be interpolated in the same way as the values of small u are. Okay, so this is one observation, and the second observation is obviously related to delta epsilon, which will also be interpolated using the same B matrix as you do for the strain itself. So delta epsilon will also be B times delta U, just as epsilon is B times U. Okay, so with that, these are our definitions. I have put these brackets here. I'll drop the brackets from now on. I have put these brackets here just to indicate that they are not tensors, but they are vectors. But most of the time we will now be dealing with vectors. So we will drop the brackets and hope that there's no confusion. But you may be more familiar with these equations from a tensorial point of view, from an indicial notation point of view, and it is not always straightforward, though in this case, in this particular case, it's easy. It's not always straightforward to convert a tensorial expression into a vector form. You have to be careful about doing that. So I will show you just one example here where we do tensorial operations systematically in order to arrive at the final vector equations. Remember, in finite elements, we all store strains, stresses as vectors, though they are actually tensors. The operations can be done in the tensorial form, and then if you are good at it, you can convert those tensorial expressions without losing their essential meaning to vector expressions. Let's see one example. If possible, I'll do a few more in the next week. So this matrix vector form is also known as the Voigt notation. As opposed to the indicial notation that we use. Now, in our Voigt notation, we have made a choice already. We have chosen that we will store in the vector, we will store the strains in this order and the stresses in the same order. So what we have actually said is the 1 component of the tensor will go to place 1 in the vector, 2 will go to 2, and 1 2 will go to 3. So this is the mapping that we have chosen. This is the indicial notation, and this is the mapping in the Voigt notation. So these are places in the array, whereas these are places in the indicial tensor notation. Now you have to look at every tensor expression that appears in your problem in order to derive the vector notation, given that this is a choice that you have made at the very beginning. This is how I'm going to store my tensor components in a vector. This is the ordering that I'm going to use. This ordering I'm not going to change. If you change this ordering, your vector matrix notations will also change. Now let us look at this product. Okay, so this is the inner product of stress and strain, which from indicial notation we know is sigma ij epsilon ij. Now epsilon ij, we know epsilon ij from the strain displacement relationship is half u I comma j plus u j comma I. This is we know. So sigma ij epsilon ij is actually half of sigma ij u I comma j plus u j comma I. This is No. So this, the right hand side is half sigma ij u I comma j plus half sigma ij u j comma I. I'm using initial notation here. Now sigma ij and sigma ji are the same because sigma is symmetric. So I can write this as sigma ij u I comma j plus half sigma j I u j comma I. But here, because this is what I'm writing is a scalar, these two expressions have the same meaning. They just have the j and I reversed, but they actually mean the same thing. They actually mean sigma 1 1 u 1 comma 1, sigma 2 2 u 2 comma 2, and so on and so forth. So then I can just add these two together and write it as sigma ij u I comma j. So this is how I can write it. Then I can write this as sigma ij. I can write the constitutive equation sigma ij c I j k l epsilon k l. Now I know that this is c I j k l u k comma l plus u l comma k. I can use the same argument here. The first term here is half c I j k l u k comma l, and the second term is half c I j k l u l comma k. So these are the two terms, and now k and l can be interchanged. So c I j k l, from the symmetries of this of the stiffness tensor, this is also lk. They are the same. So Cij Lk Lk, and this is Cij Kl Ukl. These two are the same terms, just with K and L reversed, but K and L are repeated indices, so we don't care if they are reversed, and therefore this will be equal to Cij Kl Uk comma L, just like this. So I will replace this with Cij Kl Uk comma L U I comma J. So this is what, and this is what I have written here. So this is what I get from doing this rather long but straightforward tensor manipulation. Okay, now we know how to take the variation of the derivatives of u. We know that del u k del l, this is uk comma l. If I take the variation of this, delta of this, I can take the delta inside and write it as del kl of delta uk, del xl of delta uk, which is same as delta uk comma l. So this is how we can write the first variation of delta ukl. So when I take a variation of this whole thing, when I take the variation of this scalar in initial notation, I will write Cijkl delta ukl, and this uij is not, I don't put a delta in uij. I do that in the second term, Cijkl ukl delta uij. So the sum of these two terms, remember the delta operates on products in the same way as the d operator does, or the del operator does. So so this is what I get when I take delta of this whole thing. And then now to handle this, we can do kind of the reverse of what we have done. So we can write this as Cijkl ui comma j delta ukl plus, and here we can use the symmetry that we have not used so far. This is a symmetry of the stiffness matrix that we know. So this term we can write as ckl ij ukl delta ui comma j. Again, kl ij all are repeated indices, so we can see that this term and this term are actually the same. So this we can write as C I J K L U K comma L delta U I comma J. It's the same thing. That's what we have done here. Again, let's take this so we can reverse what we did. C I J K L U K comma L is equal to half C I J K L U K comma L plus half C I J L K U L comma K. But C I J K L and C I J L K are the same, so I can write this as C I J K L UK comma L plus UL comma K, and this would then become CIJKL epsilon KL equal to sigma ij. So this term here is sigma ij. Again, then I have sigma ij del ui comma j, 2 times that. So let's take sigma ij del ui comma j, which using the symmetry of sigma is sigma ij del ui comma j plus half sigma ji del uj comma I, which will lead to sigma ij into half del ui comma j plus del uj comma I, and now I define this part to be my delta epsilon ij. So if I do that, then this becomes sigma ij delta epsilon ij with the two I have not touched, so the 2 remains. Now you could have said that epsilon ij is equal to half ui comma j plus uj comma I. This I know. If I take the first variation, if I take the first variation of epsilon ij, I of course get this. But this is obvious, and you would be right. This is obvious in this case, but in many cases it's not obvious, and it's always a good idea to do the tensorial manipulation first and then translate it into the vector notation. How do we do that? So one thing you already see here is that this 2 is a surprise, because this is not exactly what you expect it to be. Let's see why. So now that I have established that, now what I have established is a delta of this quantity is equal to 2 times sigma ij. I have to go back to the stresses and strains that I'm using in my problem, which are sigma xx, sigma yy, and sigma xy. So this will translate to 2 times sigma xx delta epsilon xx plus sigma xy delta epsilon xy plus sigma yy delta epsilon yy, and then sigma yx delta epsilon yx. Remember, you cannot forget this term. If this is there, this has to be there as well. But these two are equal because these are symmetric, so I put a 2 here. Club the 2 with the strain, not with the stress. So I can get rid of this by putting this 2 here. So now if you look at this, this can be written as, in terms of our vector notation, as 2 times sigma delta epsilon xx delta epsilon yy. This is the ordering that we have done. 2 times delta epsilon xy So this is how we can write this expression, and therefore this expression. Okay, so this is 2 times delta epsilon transpose sigma, not just delta epsilon transpose sigma, as you might think when you look at this expression. It's tempting to write this expression as just from this expression, it's tempting to write this as delta epsilon times sigma, but this 2 comes out correctly because we have gone through this rigor. That is one thing. The other thing that is important in this is that the definition of the first variation of the strain or some strain like quantity may not always be obvious from the strain displacement relation, and if we go through these steps, we get the correct definition of the first variation of certain quantities. If we go through the steps using indicial notation, we sometimes get the correct, we are able to get the correct definition of some of these quantities, which will help in avoiding problems later. So just remember this, that we have just proved that this is equal to 2 delta epsilon times sigma. And now let's go back to our principle of minimum potential energy. Try to write the potential energy. The potential energy over the element is an integration over the element volume of sigma ij epsilon ij, half of that, minus the potential of the loads, that is the body forces and surface tractions. Surface tractions come in only if the element has an edge, element shares an edge with the boundary of the body, otherwise not. Otherwise this term is 0. So now here you have the half, and we already know that when we take delta of this, take delta of this, delta of this, and delta of this. Delta of this is bi delta ui. Delta of this is ti delta ui, and we are storing this ti as so delta u we are storing as delta u delta v, and t we are storing as tx ty. So this would be the matrix representation of this. Similarly, this would be the matrix vector representation of this. And this we have proved that this is equal to 2 times delta epsilon transpose sigma. So the 2 and this half cancel out, and this is the first term that we have. So we are putting, remember, delta pi equal to 0. So we do delta here, put it equal to 0, take these 2 terms on the right hand side, and this is the expression that we have. This is what we have to satisfy. This is the variational statement that we have to satisfy. And now the steps are exactly the same. Delta epsilon transpose, remember delta epsilon is b times delta u. So delta epsilon transpose is delta u transpose b transpose. That's what I have put here for this term. Then for sigma, I am using sigma is c times epsilon, and epsilon is b times u. So I am putting in place of sigma this guy. Similarly, delta u is n times delta capital U, which means that delta U transpose is delta capital U transpose n transpose. So I have n transpose B here from this. I have n transpose T here from this. So now I make this usual assumption that delta U is an arbitrary quantity. So I can take it outside. U does not depend on this V, so U can be taken outside as well, and I'm left with this part. Here also delta U transpose is taken out, and I'm left with this part. Since delta U transpose is arbitrary, we must have this equal to this, and B transpose CB integral will give me my Ke, the local stiffness matrix for this element. This would give me the body force vector, the nodal equivalent body force for this element, nodal equivalent surface traction, which will come into play if SE shares a boundary with delta VT. If SE shares some part of delta VT, then only this comes into picture, otherwise not. So this is then my finite element discretization. This is the local stiffness matrix for this three-noded triangular element. And now I will do the usual assembly to get the global stiffness matrix. If my mesh consists only of these triangles, then I can just use the assembly procedure as we have learned it to get the global stiffness matrix, put the boundary conditions, and solve. So from now on, we will assume that you understand the assembly process, the process of putting in boundary conditions and solving. You understand all that. Uh, Assuming that, we will now only concentrate on finding the local stiffness matrix, deriving the local stiffness matrix. And that is what we will do in a problem for three-noded triangles in the next lecture.